Hi, everyone. We're on day 3. I hope everyone's happy, having a good time, enjoying the talks, learning a lot, getting to connect with mentors, speakers, sponsors. I think actually I'm going to start off with just saying this event is really for you. We hope you're enjoying it. We're very open to feedback. This is the first time we run MenaML. And we would love to hear from you. So I think some of you have come up to us and shared some feedback and that we've actioned. So I hope you're happy with the bus at 7:45. I hope you're happier with the food today. We're sending you at the end of each day a form. Feel free to fill it in, give us feedback, or just come talk to us. Hello. Sorry, we're starting a bit late. I think you know that today is National Sports Day in Qatar, so transportation is very off. So thanks for bearing with us, and sorry we're starting a bit late. We will be pushing this session for 15 minutes later, and then the next session will start at 10:45 instead of 10:30. The last thing I want to mention, Friday is a short day. It's only 2 hours. We'll be ending at 11:30 in times for prayers. So push through. We're Tuesday. We still have 3 full days to go and a quarter of a day on Friday. Okay. I will now introduce our next speakers. So I'll start with Safa. Safa's research is centered around safe AI, generative models, and reinforcement learning, and motivated by applications in computer vision and health intelligence. Safa obtained her PhD in electrical and computer engineering from the University of Illinois at Urbana-Champaign, working with Professor Alexander Schwing. She graduated with the Bachelor's and Master's in electrical engineering and information technology from Technical University of Munich. She obtained a master's degree in computer engineering from Virginia Tech, advised by Professor Sandeep Shukla, and she was a visiting scholar at UC-Berkeley, where she worked on her master's thesis under the supervision of Professor Alberto Sangiovanni and Professor Andreas Herkersdorf. Sorry if I'm not saying it right. And the next speaker for this same session, they're co-leading, will be Andrew Qadi. Andrew is a research engineer. Andrew, raise your hand. He's a research engineer with us at Google DeepMind and one of the authors of GenCast, and he'll tell you a lot about it. He completed his Master of Engineering in Mathematics and Computer Science at Imperial, where he focused on quantum algorithms and satisfiability problems. And his current work focuses on scaling and operationalizing machine learning weather models, recently working on GenCast. So the talk now is on diffusion models, and I'll hand it over to Safa to kick us off.
Good morning, everyone. So let's start with a small challenge. Let's say somebody gives you a set of images drawn from some mysterious unknown distribution, and your mission is to create some similar images without ever seeing the rule book for image generation. How would you go about that? Any ideas? Okay, so there are 2 main strategies in the literature. Does it help? Okay, I'll tell you. So the first strategy is to try to approximate this data distribution via some easy to sample from distribution that we denote by Q theta. Theta are the parameters of this distribution. And in deep learning, we generally model Q theta as a deep net. And theta here would be then the parameters of this deep net. The second strategy is to skip all the math gymnastics and directly learn to sample from this Q theta without ever explicitly modeling it. Then, once we have either of these models, at inference time, what we want to do is to sample from Q theta, and we want these samples to be as real as possible. Let's try to further better understand generative models by comparing them to discriminative models. So in discriminative modeling, we want to learn to classify some input x. We want to basically assign a label y to this input x. For example, x is an image, and y would be a class, for example, cat, dog, bird, etc. Formally, we want to learn the distribution of labels given inputs, p of y given x, and this translates into learning some decision boundary between samples belonging to these different categories. And this decision boundary can be linear, can be nonlinear, depending on how you choose to model p of y given x. In contrast, in generative modeling, we want to learn the underlying distribution of the data, so P of X, or P of X given some label Y. For example, we want to generate images, but we want them to be bird images. This is a more challenging problem, as you see. So X can be continuous, can be discrete. It's high dimensional most of the time. Think of images. So why do we want to do this? Why? Any idea? I want this to be interactive, actually, to be able to sample from it, because we might want to generate some images, some text, some images given text, right? So in a nutshell, you can think of discriminative models as being some sorting hat trying to sort objects into categories, and generative models being some AI wizards trying to create some brand new data from thin air. All right, so probably you've noticed that in the last couple of years, there have been an exponential growth in the capabilities of generative models. So now they actually are impressive at capturing the intricacies of real data distributions. It almost feels like magic sometimes. For example, talking about magic, I asked Sora, the latest OpenAI model for text-to-video generation, to imagine what you guys all look like. And this is what it thinks. So I just had to give it the input prompt. Students from the MENA region are attending a winter school in Qatar, and it looks pretty real, right? Pretty close. Or did it give some of you an AI makeover? So actually, when I was an undergrad, when I was an undergrad, I also attended a winter school. It was at a much smaller scale, but it was so fun that eventually we composed an entire song about the school for the closing ceremony. So I thought, why not try to do the same for you guys with AI? All what I had to do is to give Sonu this prompt, and boom, it generated a MenaML anthem for me. Do you want to hear it? So in my opinion, this was so impressive. Who wants to hear it? Okay. We listened to it for like 51 minutes.
Flying high like eagles to the heart of desert breeze. School of dreams in Qatar. Learning algorithms with ease. From Cairo to Casablanca, students flock from far away. Notebooks packed with visions, ready to code night and day.
I hope you're doing that in the practice. Okay, I'm gonna share it with you in the WhatsApp group so that you can listen to all of it. Actually, pretty cool. Do you like it? Okay, so Sunu is actually a diffusion model, but the family of Gen AI models is broader. It has many members. For example, we have normalizing flows, variational autoencoders, autoregressive models, GANs. But at the core, they're all trying to pull off the same trick. So they're all trying to learn some way to map noise into some meaningful samples that look real. In GANs, this mapping, F theta, is called the generator. So you can think of it as an AI artist that tries to get better at generating data by trying to trick a critic. And the more it tries, the better it gets, the more real the samples get. In case of variational autoencoders, this F theta is called the decoder. So basically here, you can think of, again, an artist that tries to memorize some sketch of images and then tries to redraw these images. And sometimes it gets the details, sometimes it adds some creative touch. In normalizing flows, F theta is a flow function. it's basically an invertible transformation. And here you can think of some master baker that tries to model and shape some dough into the perfect croissant while making sure that volume is preserved and the transformations are smooth and reversible. In case of diffusion models, which are the first version of this is called denoising diffusion probabilistic models, we're trying to do something slightly weirder. We're trying to actually inject noise to real data, and then we're trying to gradually reconstruct the images. Sounds weird, right? Sounds more complicated. So this is what this talk is about. We're gonna understand why all of this makes sense. Can you actually think of other ways of transforming noise into samples? If you think of other ways, you should write a paper about it. Okay, cool. Let's dive in. So in diffusion models, as we said, we have two processes. We have the forward process that takes in an input sample x0 from the real unknown data distribution Q of x0, gradually injects noise until it's completely corrupted. So eventually we get x capital T, which is pure noise, drawn from some pure noise distribution Q x capital T. And then the second process we talked about is called the backward process. That's a generative process where we're trying to draw some noise and gradually try to reverse the noise we injected in the forward process in order to reconstruct something that looks like real images. So now at the first glance, you might be wondering, okay, this looks very similar to GAN's, at least the backward process. We start from some noise, transform it into some samples. So, and you showed us some impressive stuff. So where is the magic happening? Well, maybe it's in the forward process, right? So the other models don't have this forward process of noise injection. Who thinks so? Okay, nobody thinks so. But let's dive in and find out. All right, so in the forward process, here we denote by x0, as we said, the real data samples, q x0, the real unknown data distribution. After one step of adding noise, we get x1 drawn from q of x1. And since we're talking about noise and noise distributions, let's denote by q xt given xt minus 1 the noise distribution. How should we model it? Any idea? How should we model a noise distribution? Gaussian, yes. So we can use a Gaussian distribution. What should be the mean of this distribution? Again, please. Y0. So it's conditioned on xt minus 1. You start from xt minus 1, and you try to add noise to it. So it probably would make sense to have xt minus 1 as the mean, right? But actually, it's not exactly what we do. We don't just copy xt minus 1. We scale it down by some constant square root of 1 minus beta t, where beta t is a scalar between 0 and 1. So what about the variance? The variance is square root, is beta t. The covariance matrix is beta t identity. So why this weird choice? Why are we scaling down xt minus 1? What happens if we don't? If we keep adding noise to the samples? Exactly, excellent. So the norm explodes, the variance explodes, and we already know that deep nets don't work well with quantities that change in magnitude very frequently. Okay? This is just another fancy way of rewriting the same thing. So to get xt, we just take xt minus 1 from the previous step, scale it down, and then add some noise to it, right? All right, so now you might be actually wondering, fine, where are you getting with all of this? Actually, for how long do we need to run this until you're happy? And also, since you're adding noise, why do we have to do it gradually? Can you just do it in one shot? It sounds easy, right? If you think so, you're right. If you don't think so, let me try to convince you. So next, we're gonna see how we can derive q x capital T, the last sample, given the first one, the data sample, in one shot. So here I just put our noise distribution and the other way of expressing it. And to compute Qx capital T given x0, let's try to express X capital T as a function of x0. So let's start simple and do it for x1 and x2 and let's see how it goes. So this is x1, I just copied this formula. I did the same for x2. Now let's plug x1 into x2. So far so good. You with me, guys? Okay, so this is what we get. All right, what's this term? Yeah, what's this term? Sum of two Gaussian variables, right? So what's the distribution of the sum of two Gaussian random variables? Gaussian 2. What's the mean? 0, right? Sum, yes. What's the covariance matrix? What if I tell you that the variables are uncorrelated? Sum of the variances, right? Okay, so this is what we get then. This looks a little bit too long, this covariance matrix, notation-wise. So let's try to introduce some notation to simplify it. Let's call this alpha 1, this alpha 2, the product alpha 2 bar, and then we can rewrite this in a nicer way. So that's what we get. And then we can actually adjust x2 to have this much simpler form. Basically, it's telling us that if you want to get x2 in one shot from x0, you just need to scale it down by square root of alpha 2 bar, and then you need to add this noise of this form. If we keep going, we can also do the same thing for any xt down the process, and we can derive the distribution of qxt given x0, and it would look like this. So now let's come back to our first question. Until when should I do this? For how many steps? We said we want to transform x0 into random noise, right? So ideally, I want this q x capital T given x0 not to depend on x0 to start with, right? How do I get rid of x0? Any ideas? Okay, I'll tell you. You seem to be too tired from working today. Kidding. Okay, so actually, if we plug in some numbers to compute this alpha bar to see what happens to it, let's say after 1,000 steps, let's say the beta t's are all around 0.5. So we said 1,000 steps. So I'm gonna get this alpha t capital T bar equal to 0.5 exponential 1,000. What's that? 0, yes. Basically, after enough steps, this alpha t bars goes to 0. Perfect. We got rid of x0, right? What happens to the covariance, 1 minus alpha t? It also goes to 1. So this q x capital T given x0 for a large enough t is going to actually turn out to be the normal distribution. Okay, great. So far I told you that you can generate the final distribution from the the distribution of the noise variable at the end of the sampling after capital T steps from the data distribution. And I told you that it's a normal distribution. So yeah, then what, right? We still didn't see any magic here. Okay, just bear with me. Maybe let me first ask you, do we actually know Qx0? Do we know it? Okay, do we know Qx1? No? Yes? Raise your hand if you think no. Yeah. Okay, no, we don't know it. Do we know Qx capital T? Yes, we just derived it. It's a normal distribution. What else do we know? Yeah, large enough, right? We also know the noise distribution. So qxt given xt minus 1. And we also know qxt given x0, right? We just derived it. So that's everything we know. All right, so now we said we didn't see any magic in the forward process, so let's check the backward process. So in the backward process, we said we want to reverse the noise that we injected in the forward process. To do that, we probably need to know how to get from x capital T to x capital T minus 1. That would be the first step, right? And for that, we probably need to know qx capital T minus 1 given x capital T. Do we know that? Who thinks yes? How? Bayes rule. Yes, very good idea. Let's try that. Okay, so this is what we get now. So we have qxt given xt minus 1. Do we know this? Yes, we know it. It's a forward process, right? Okay, what else do we know? Qx capital T, right? What is it? Normal distribution. All right, what about this guy? We don't know it, right? You're convinced we don't know it. Okay, cool. So unfortunately, Bayes rule didn't work out. Any other ideas? Okay, so let's try something else. Since we can't compute qx capital T minus 1 given x capital T, what do we like usually to do in machine learning? Yes, exactly, approximate it using some other distribution that we learn end to end. So we model this as p theta of x capital T minus 1 given x capital T. Now, how should we model this? Which family of distribution? Do you have any constraints? How, like, what do we want this p theta to satisfy? By Gaussian. But the reverse of a Gaussian is not a Gaussian. Louder? Bayesian? Fisher distribution. It can be actually anything you like, but there is one constraint. It has to be easy to sample from, right? Because this is what we want to use it for. We want to use it to eventually apply it sequentially and then eventually generate a sample that looks as if it was generated from the data distribution, right? So pick your favorite distribution that we can easily sample from. And I'll go with your suggestion. Who said Gaussian? So let's go with that. Actually, that's what's used usually. Okay, so what should the mean of this distribution be? Xt minus 1, xt, yes. But probably let's give it more flexibility and say it's a function of xt and time t, right? What about the variance? I have the answer here, but you need to justify it. Shall we learn it too? Shall we not learn it? Why not? Yes, so basically, the information, the structure of the data is encoded in the mean. Usually the variance captures some uncertainty. So we believe most of the information is in the mean. But it wouldn't have harmed, right, to write a variance, or would it have harmed? Actually, it would have harmed. Because imagine what would have happened if, in the learning process, this covariance matrix explodes. Right? The loss will diverge and nothing will work out. Optimization might become very hard, right? So that's why here we're keeping it to be like a small noise. All right? Okay, so now we agreed on how to model this reverse denoising process. So how are we gonna train it? What's your favorite loss? That wouldn't be the first thing I would think of, right? So I would think of maximum likelihood, because here we're given some samples, we're given the model that we want to use, so I would think of MLE. So this is the MLE loss. You're all familiar with it, right? Can we actually compute the likelihood of x0 under this model? Do we have a formula for that? Do we know how to compute P theta of x0? We know of, okay, we actually, let's see, we might know it. So what we know is the joint distribution, because we can factorize it as follows. So we know P theta x capital T, and we know the stepwise backward distributions, right? But what do we need to do to get P theta of x0? We need to marginalize, right? Okay, is this tractable? Who says yes? Who says no? Yes, it's not tractable. Why? So let's try to understand how many configurations we need to sum over. We said capital T is maybe around 1,000. X is, let's say, an immersion. Let's not be too dramatic. Let's say here we're talking about some easy benchmarks. Let's say CFAR 10, so we have X1 of dimensions 32 by 32 by 3, 3072, I think. And then for each of these pixels, we have, it can take values between 0 to 255. So I think at this point, you believe me, right? It's a huge number of configurations that we need to sum over, so it's computationally intractable. Okay, that's a bit sad, right? So we can't compute P theta of x, and we can't use maximum likelihood loss. What else can we do? Yes? Yes, okay. So we're gonna lower bound, actually. We're gonna lower bound the log likelihood with some other loss, and we're gonna make this lower bound tight by maximizing theta so that it approximates our beloved log likelihood well enough, right? So let's see how we can do this. We can start with computing the KLD between the joint distribution of the backward and reverse process. And if we massage it a little bit to extract the log likelihood out of it, we get this exact equivalence. And then now again, let's try to understand what we have and what we don't have. Do we have this term? Okay, this is KLD. Do we have this term? This is the forward process, right? Do we have this term? Yes, no, no. Why? This is the backward process. Like, this is just a joint distribution. I can factorize it to be equal to x p theta x capital T multiplied by p theta x capital T given x capital T minus 1, right? So I can compute this. What about this term? This is the backward process conditioned on x0. So we usually know how to condition on x capital T, but not x0, right? So let's rewrite this to make it clear. So if we use the base rule here, you will see that the denominator is actually p theta of x0, which in the first place what we're trying to avoid, right? So unfortunately, we can't compute this. We can't compute the KLD, but the good news is that the KLD is always positive, so we can derive a lower bound to the log likelihood, and it looks like this. Okay, this is some progress. This is still not the elbow loss. It's missing something. It's missing the expectation over Q of x0. So let me add it, and here is the elbow loss. Okay, cool. So just some massaging, and we get this form. If we have a closer look at it, we'll see that the first term is not related to theta, so we can ignore it. The last term is very easy. That's just like the decoding process starting from the sample before the last step in the backward process. And this term here, let's try to understand it. So this is just a cheat sheet or from a cheat sheet. So this p theta xt minus 1 given xt is, as you see, the backward process. This one, let's try to rewrite it. So it can be, using the base rule, it can be rewritten to be equivalent to what we have here. And if you have a closer look at this, these are just quantities from the forward process, right? So we can compute it, and actually everything is a Gaussian. So this quantity q xt minus 1 given xt x0 is also a Gaussian, right? And if we do some math, we can actually derive the closed form expression of the mean, and this is what it's equal to. And if we plug in the normal distribution formulas into both p theta and q above, we get something like this. So this term here, the most important term in this elbow loss, is just the mean square difference between the mean that we derived and the mean we're trying to learn from the backward process. That's interesting, right? Okay, so let's see what else we can do. Actually, we know the formula of this mean that we computed. And now the question is, can we come up with a better way to model this mean that we're learning? We can, actually, the choice is very obvious. We can actually just follow the same form of the mean that we have from the forward process. And we can, instead of modeling the entire mu theta, we can just model the noise, right, in the reverse process. And then the loss becomes this. So following your intuition, actually now we have the mean square error between the loss that, the noise that we injected in the forward process and the noise that we're trying to learn. So if actually all these diffusion models, this is where the magic is happening, is trying to learn to denoise at every step. It's trying to predict which noise did you inject in the forward process. That's it. And then all this jazz about elbows and everything, in the loss, it only shows in the constant in front of this mean square error. Surprising, right? And actually, in practice, what works is setting this lambda to 1. So we completely ignore all the jazz that we did right now. That's, you know, a bit surprising, right? Any intuition? Oh, I think we don't have time, right? Okay. Okay, so in practice, this is how the loss looks like. So instead of having that sum, we can just sample a time t uniformly. And then we sample x0 and some noise. We compute xt at time t. And then we feed it into some deep net model to get the noise epsilon theta that we're predicting. And then we have some mean square loss that we can compute using the noise we injected and the loss we predicted. And that's it, basically. And then during inference, we need to sample some real-looking samples, right? So we have the theta stars that we learned. We compute this epsilon theta star. Then we compute the mean. And then we compute the sample, like one step backward. And that's basically it. And we keep doing this until we get some real-looking samples, right? So this is an illustration of how it looks like. All right, Maria is not telling me to stop, so I'll continue. Okay, sure. Yeah, actually, I only have 2 more left slides. I wanted to add this because the popular models are the conditional ones. So what we've just went through are the unconditional models, but we can easily add some conditioning, for example, over text. That would be the C here. So basically, the C would just be an input to the network that learns the noise. And C can be of different types. We can condition on some scalar. For example, I wanted to generate images of class cat for me, or I wanted to generate an image given this textual description, or maybe given some layout of how I want this image to look like. Like, for example, I want the sun to be in the corner and the house in the middle, something like that. Okay, so if you want to condition on a scalar, the way or the most obvious way to do it, inside of this deep net that predicts the noise, you take the feature maps and then you take the label. For example, cat, you encode it, one-hot encoding, for example, you embed it into a representation, and then you broadcast this representation in the feature map. So very intuitive. What if you have a text? Here you have cross-attention, and I believe Ihsan talked about this in his talk. So all what you need to do is to learn like some tokens, or to embed the image into tokens, use this as your query. You do the same for text, and there you get some keys and values, and then you use cross-attention to predict some output tokens, and eventually, if you keep doing this, you will get some images that are conditioned on the text. Okay, so that's it from my side. Thank you so much. So Andrew is going to talk more about some impressive applications. So
thank you. Sorry, I think we just need to switch the screen over. Is it? Yeah, if you want to actually take some questions, apparently there's something wrong with the recording.
Okay, any questions? I asked you many questions, but you guys, yeah. Yes, please. Sorry. Yes.
Depending on the noise schedule you use, it kind of biases the loss towards perceptual aspects of the data. Do you have any sort of comments on that? Or
Yeah, so the intuition I have about that is to make sure that the scale of the different terms in the chain is kind of the same, because usually the beta T will follow a decreasing schedule. So that lambda T will become smaller and smaller through the process. And if you're using the same learning rate for all these like different blocks, like if you're using just a sum and one learning rate, then you're not gonna pay enough attention to the to the blocks that will come at the end. So that's the intuition I have. So instead of, let's say, using the loss that I presented later on, where you sample T, and you adjust the learning rate for at every step in the chain, you just completely remove that constant to make sure that everything has like some equal weight. That's the intuition I have.
yeah,
Maybe you have different.
I think what you can show is that if you plot the actual loss you get with lambda T set to 1 and lambda T not set to 1 for the same schedule, that you focus the attention of the learning, like basically the loss is higher in the points when there's the most perceptual difference. So it kind of is actually a way of kind of biasing diffusion models to care about the things that humans can see, which is part of the reason they work so well for images. And yeah, this is something I'm going to give a talk on Thursday about a similar model called Bayesian flow networks, and I'll kind of, yeah.
Okay, looking forward to it. Thank you. Any other questions?
Yeah.
Okay, maybe after Andrew's talk.
Can I ask one question, just quickly? I want to understand, like, in the backward process, we go from xt to x0. We do it in steps, like similar to how we do it in the forward process. I've tested this, like if we go in one step, it doesn't give us a good result. Like it's like an average of all the things that the model has seen. And why is that? Like what's the intuition behind this? Like why do we go in steps in the backward process?
Yeah, so if you look at the loss, actually, it turns out that the entire derivation is based on the fact that we do it stepwise and we reverse the noises stepwise.
So if we make the forward process one step, it will like converge to a GAN, like
yeah,
okay.
Yeah, so I think I have a long answer to your question. So this noise epsilon is correlated to the score function. So, and the score function, it's not really the score function, it's the score function at every time t. It's the score function of the noisy data. And if you actually follow that, it will smoothly lead you to the manifold. So
okay, so it's like kind of an optimization.
Yes, okay. It's a way to guide the sampling towards the manifold in a smooth way.
Understood. Yeah.
Okay. Thank you.
Yeah, like if you think of your gradient descent, you find the gradient, you take a little step, you recompute, take another little step. If you try to just follow the gradient at the point you're at, you're going to go off the curve instead of where you want to go to.